All right, let's conclude with some remarks, or rather with the generalization of what we just did. And let's call this what happens if we have different sample sizes. Now imagine, even if you're OK with assuming everything we've assumed so far, namely that we have two groups, the group X with n samples that are Bernoulli, so a group X, which is Bernoulli and all the samples are RID, and a group Y, which is Bernoulli and all the samples are RID, it might be hard in practice to actually find any such setup where the sample sizes of both groups are equal. Often you'll have different sample sizes. So what might happen is that you have x1 up to xn1 and y1 up to yn2. And you still want to compare whether the proportions are equal. So the question is, what's a reasonable test statistic here? The problem is the asymptotics of this are a little bit trickier, just because you have two parameters and you have to say something about what happens asymptotically with those parameters. So a standard assumption would be that they both go to infinity, but then you need to fix a ratio and so on. So you need to somehow say what happens with the relative proportions of these two as they increase. And we're not going to cover this. But one thing we can do, namely, we should think about what should our test statistic look like based on what the central limit theorem actually does. So let me first write down the central limit theorem again. So let's assume we have z1 up to zn IID random variables following some distribution. And the only thing we need is that they have an expectation. And let's also assume, expectation of zi is mu, let's say. And let's also say they have finite variance. And call that variance sigma squared. Now, the central limit theorem tells you that if you zoom in, if you multiply by square root n, zn bar, where zn bar is the average of your values, you subtract off the mean, and you divide by square root of sigma squared. Then this in distribution goes to a standard normal. So let's assume these are real random variables. So they live in R. OK, now, so in order for something like this to be asymptotically normal, what we always have to do is we have to subtract off the mean, and we have to multiply by square root n and divide by the square root of the variance. So what are we actually doing here? Asymptotically, we need a random variable that has mean 0 and variance 1. And actually, both these steps, subtracting off the mean and what we're multiplying with, serve to make this whole random variable here have mean 0 and variance 1. So how can we see this? Well, let's compute the expectation of zn bar, which is 1 over n, because I'm dividing by 1 over n, and then by linearity of the expectation, I have sum I equals 1 to n expectation of zi, which is n times for the sum divided by n times mu is mu. And this is exactly what I'm subtracting off. So at the end of the day, this is mean 0. And then for the variance, I have a sum of independent random variables here. So 1 over n pulls out as a square. So I have 1 over n squared. Then I have a sum of all the variances of zi, which is, again, because they are all the same, they all have the same distribution, it's n times n divided by n squared times the variance of zi, which is 1 over n times sigma squared. Great. So, and that's exactly what we do here. We divide by the standard deviation, by the square root of the variance. And this is where the n comes from, and this is where the square root of sigma squared comes from. So in other words, this thing here has expectation 0 and variance 1. So now let's think about what we would want to do to Tn here. Or in other words, let's start with the same reasonable guess of a test statistic. So now what we would like to do is we would like to consider Px hat. This is a consistent estimator as long as n1 somehow goes to infinity. And Py hat, this is also consistent estimator as long as n2 goes to infinity. And this under h0 will also have mean 0. So the only thing that we have to do to at least ensure these two conditions, if we're forgetting about all the limiting things that are going on to make the CLT work, at the very least, what we want is we want to write down, at least asymptotically, but here we can do it exactly, a random variable that has mean 0 and variance 1. So mean is already 0 under h0. So the only thing that is missing is we need to rescale this so that its variance is 1. And this we can do. But I'll leave it up to you, actually. So now the task. So let me first write down exactly what I mean by this. So Px hat is now 1 over n1, the average of my xi's, and Py hat is the average of my y's. Of course, up to n1, up to n2. So now, how about you try to calculate the variance of this expression, right? Because this is what I would have to normalize by. And of course, this will depend on Px and Py, which I'm assuming to be equal here. So let's say under h0. And we will need a plug-in estimator, but actually, the plug-in estimator under h0 will still be fine. It's still going to be consistent if I just average out my two proportions that I estimate here. But the important thing is, how do n1 and n2 enter this calculation? And yeah, and this is exactly given by the variance. And the estimator, then you can write down the associated test statistic, and this is what is commonly known as the test statistic for a comparison of two proportions. Okay, and with this we conclude.